On October 17th, 2025, something traveled from another star system, passed within striking distance of Mars, and then completely disappeared from Earth's view. For weeks, nobody on our planet could see it. And when it finally came back, scientists realized we'd been blind during the most important moment. This is the story of 3I divided by Atlas, only the third confirmed visitor from beyond our solar system. A comet so ancient it was born before our sun even existed. It came screaming through space at over 58 kilometers per second, threading past Venus, Mars, and Jupiter with what some researchers called unsettling precision. And right when it reached its most active phase, belching out massive amounts of gas and dust, Earth went dark. We couldn't see anything. But here's the thing, some spacecraft kept watching, and what they saw changes everything we thought we knew about interstellar visitors. Opening the mystery, let me paint you a picture of July 1st, 2025. The Atlas Survey Telescope in Hawaii was doing its normal routine, scanning the sky for asteroids and comets that might pose a threat to Earth. Nothing special. Just another night of automated observations. Then the computer flagged something. At first glance, it looked like a comet. There was a fuzzy glow around a bright center, what astronomers call a coma. Standard stuff. Except this one was moving wrong. Way wrong. Most objects in our solar system follow predictable paths. They orbit the sun in ellipses, coming back around every few years, decades, or centuries. Their orbital eccentricity, basically how stretched out their orbit is, ranges from 0 to just under 1. A perfect circle is 0. A really stretched ellipse might be 0.9. This thing had an eccentricity of 6.1. Let me be clear about what that means. An eccentricity above 1 means the object isn't orbiting at all. It's on a one-way trip through our solar system. It came from somewhere else, it's passing through, and it's never coming back. And 6.1? That's not just hyperbolic. That's the highest eccentricity ever measured for any object visiting our solar system. The velocity made it even more obvious. This comet was traveling at approximately 58.61 kilometers per second relative to the Sunday. For context, most comets born in our solar system top out around 40 to 50 kilometers per second when they're really hauling. This thing was moving like it had somewhere to be. Within days, astronomers around the world confirmed what the Atlas team suspected. This wasn't a local. This was our third confirmed interstellar visitor. They named it 3I divided by Atlas, with the 3-1 standing for third interstellar object. The first was Oumuamua in 2017, that weird cigar-shaped thing that sparked 1,000 alien theories. The second was Borisov in 2019. A more normal-looking comet that behaved pretty much as expected. But 3I divided by Atlas? Right from the start, this one was different. Act 1. The Pre-Discovery Ghost. Here's where things get weird, and I mean really weird. Because technically, we discovered 3I divided by Atlas on July 1st. That's when the Atlas survey flagged it and humans first became aware of its existence. But something else had already been watching it for weeks. Something that wasn't designed to find comets at all. NASA's TESS, the Transiting Exoplanet Survey Satellite. This thing hunts for planets around distant stars by watching for tiny dips in brightness when a planet passes in front of its star. It's basically staring at the same patches of sky for weeks at a time, taking image after image after image. And buried in all that data from May and June 2025, months before anyone knew 3I divided by Atlas existed, there it was. A team of researchers went back through the TESS archives and found a faint trail of light creeping across the images. They had to stack hundreds of 200-second exposures together and correct for the Earth's movement and the satellite's orientation. But once they did, there was no mistaking it. The comet was already there, already active, already brightening as it approached the inner solar system. They calculated its absolute magnitude, basically how bright it would be if you could see it from a standard distance, and watched it change from about 14.3 to 13.7 over those weeks. That might not sound like much, but in astronomy terms, that's significant brightening. The comet was waking up. Think about this for a second. We have a space telescope that's not even looking for comets, accidentally recording the arrival of an interstellar visitor weeks before anyone on Earth knew it was coming. It's like finding out your home security camera caught footage of someone walking by your house before they even knocked on your door. But here's the really interesting part. The test data showed the comet was already active at enormous distances from the sun, distances where most normal comets are still frozen solid. And that gave scientists their first hint that 3I divided by Atlas wasn't going to play by the usual rules. Act 2. The chemistry puzzle. Fast forward to late July and early August. Telescopes around the world were now locked onto 3I divided by Atlas, and spectroscopy data started rolling in. Spectroscopy is basically breaking down the light from an object into its component colors, like a prism splits sunlight into a rainbow. Different molecules absorb and emit light at specific wavelengths, so you can figure out what something is made of just by looking at its spectrum. The early spectra from 3I divided by Atlas were confusing. There was definitely a coma, that fuzzy cloud of gas and dust around the nucleus. You could see it in images, spreading out for thousands of kilometers. But when astronomers looked for the usual suspects, the molecules you'd expect to see in a comet's coma, they found almost nothing. CN, C2, CO+, these are the standard emission lines you see in comets. They come from organic molecules breaking apart in sunlight. Every comet from our solar system shows these features once it gets active. They're so reliable that astronomers use them as tracers to figure out how active a comet is and what it's made of. 3I divided by Atlas had barely any of them. Instead, there was dust. Lots and lots of dust. The comet had a visible dust coma, but the gas composition looked all wrong. It was like seeing smoke without fire. You don't usually get significant dust production without the gases that push it off the nucleus. Several research teams proposed explanations. Maybe the surface of the nucleus was covered in some kind of processed crust, material that had been altered by millions or billions of years of cosmic ray bombardment and UV radiation. When sunlight warmed this crust, it might crack and fracture, releasing dust without the usual gas emission, kind of like watching dry dirt crumble when it heats up. Another theory involved hypervolatiles, substances that evaporate at extremely low temperatures. If the comet's nucleus had pockets of these materials near the surface, they could sublimate and push dust out into space at distances where normal ice would still be frozen solid. This would explain why the comet was active so early, and why the normal gas tracers were missing. But the real answer wouldn't come until September, when the James Webb Space Telescope turned its infrared eyes toward 3I divided by Atlas. And what JWST found was stunning. The NIRSpec instrument caught a detailed spectrum of the coma, and there it was in the data, clear as day. Carbon dioxide. Not just a little bit, a massive amount. The CO2 to H2O ratio, carbon dioxide compared to water, came in at 7.6, with a margin of error around 0.3. To put that in perspective, that's among the highest CO2 to water ratios ever measured in any comet anywhere. Most comets from our solar system have way more water than carbon dioxide. Even the CO2-rich ones rarely break a ratio of 3 or 4 to 1. But 3I divided by Atlas was pushing 8 to 1. It was basically a frozen CO2 machine with some water ice mixed in. JWST also detected water ice, carbon monoxide, dust, and tentative traces of OCS, carbonyl sulfide, a more exotic molecule. But CO2 dominated everything. The comet was essentially breathing out carbon dioxide as it warmed up. This composition told scientists something profound about where 3I divided by Atlas came from. In the disk of gas and dust around a young star, what we call a protoplanetary disk, different materials freeze at different distances from the star. Water ice forms at a certain distance called the snow line or ice line. CO2 freezes out farther away at the CO2 ice line. CO freezes even farther out. If a comet forms with this much CO2 relative to water, it probably formed near or beyond the CO2 ice line in its home system. That suggests 3I divided by Atlas was born in the outer regions of an alien solar system, far from its parent star. Or alternatively, its surface was heavily processed over billions of years by harsh radiation, driving off lighter molecules and concentrating the CO2. Either way, this wasn't a typical comet. Not by our standards anyway. Akht Dri, an ancient wanderer. While chemists were puzzling over the composition, dynamicists were running models on the comet's trajectory and velocity. Where did this thing come from? How old was it? And how did it end up here? A team using something called the Tau High Oxford ISO population model plugged in all the data, the velocity, the direction it came from, the trajectory through the solar system. These models simulate billions of interstellar objects getting ejected from their home systems and wandering the galaxy for millions or billions of years. They track how gravitational interactions with stars and planets alter their paths and velocities over time. The models spit out a number, 7.6 billion years. That's not a typo. The most likely age for 3I divided by Atlas, based on its kinematics, was around 7.6 billion years. For reference, our entire solar system is only about 4.6 billion years old. Earth itself is 4.5 billion years old. 3I divided by Atlas was born in another star system before our planet even existed. Let that sink in for a moment. This comet has been drifting through interstellar space for longer than our world has existed. It formed around a star that may not even exist anymore, got kicked out into the void, and wandered for billions of years through the dark between stars until, purely by chance, it happened to pass through our neighborhood. The model also predicted that objects with 3I divided by Atlas's velocity and direction should have relatively high water mass fractions. Essentially, they should contain a decent amount of water ice. And sure enough, infrared observations detected water ice grains in the coma. So the model's predictions lined up with reality. But here's the paradox that fascinated scientists. This comet is ancient. It's been exposed to cosmic rays, UV radiation from distant stars, and all the hazards of interstellar space for billions of years. That kind of exposure typically processes and alters surface materials, breaking down complex molecules and creating a radiation-damaged crust. Yet 3I divided by Atlas still had relatively fresh ice. It was actively sublimating water and CO2. It had a vigorous coma. It didn't look dead or inert like you'd expect from such an old object. The leading explanation was that the comet had a protective outer layer that processed radiation-damaged crust that kept the interior relatively pristine. As sunlight heated the nucleus and the crust warmed up, it began to crack and flake off, exposing fresh ice underneath. This fresh ice then sublimated rapidly, creating the dust and gas we were seeing. It was like watching a 7.6 billion-year-old time capsule slowly opening as it heated up. Act 4. The brightness surge. Throughout August and September, amateur and professional astronomers tracked 3 I divided by Atlas as it moved deeper into the inner solar system. And something strange started happening. The comet was brightening fast, way faster than it should. There's a pretty straightforward relationship in comet science between distance from the sun and brightness. As a comet gets closer to the sun, it gets more sunlight, warms up more, sublimates more ice, releases more gas and dust, and appears brighter. You can model this relationship and predict how bright a comet should be at any given distance. For 3 I divided by Atlas, the models predicted the comet should brighten by a factor of about 1.5 as it approached perihelion, its closest point to the Sunday standard physics. Standard geometry. Nothing surprising. Instead, the comet brightened by a factor of 5. Multiple independent datasets confirmed it. Different telescopes, different observers, different methods of measurement, they all showed the same thing. The comet was putting out 5 times more light than it should, based purely on getting closer to the Sunday. Something else was going on. The term astronomers use is supergeometric brightening. It means the brightness increase exceeds what you'd expect from geometric factors alone, and it pointed to one conclusion. The comet was undergoing a major activity surge. Its outgassing rate was increasing dramatically as it approached the Sunday. This made sense given the CO2-dominated chemistry. Carbon dioxide is what scientists call a supervolatile. It sublimates, turns from solid to gas at much lower temperatures than water ice. As sunlight began penetrating deeper into the nucleus and warming up those CO2-rich layers, they started venting rapidly. The more they vented, the more cracks and fissures opened in the surface, exposing even more CO2, creating a runaway effect. It was like watching a pressure cooker start to vent. The closer the comet got to the sun, the more violently it reacted. But here's where the story takes its most dramatic turn. Because just as 3 I divided by Atlas was ramping up to its most active phase, just as it was brightening beyond predictions and preparing for its close approach to the sun, Earth lost sight of it completely. Act 5. The Vanishing Act. October 17th, 2025. 3 I divided by Atlas made its closest approach to Mars, passing the planet at a distance of about 30 million kilometers. In cosmic terms, that's close. Really close. Close enough that Mars-orbiting spacecraft had a front row seat to the show. And then, from Earth's perspective, the comet disappeared. Not because it exploded, not because it broke apart, but because of simple, cruel geometry. 3 I divided by Atlas was heading for perihelion, its closest point to the sun, at a distance of about 1.4 astronomical units. That's just inside Mars's orbit. And as it approached perihelion in late October, the comet moved to the far side of the sun as seen from Earth. Imagine you're standing in a field, and someone is walking around a large building. At first, you can see them. Then they walk behind the building, and you can't see them anymore. Not because they vanished, but because something big and opaque is blocking your view. That's what happened with 3 I divided by Atlas. The sun, this massive, blindingly bright object 1.4 million kilometers wide, moved between Earth and the comet. For ground-based observatories, trying to observe something near the sun is nearly impossible. The scattered sunlight in Earth's atmosphere creates what astronomers call the solar exclusion zone, a region around the sun where you simply can't point telescopes because the sky is too bright and the light pollution too severe. Even space-based telescopes struggle because the sun's glare can damage sensitive instruments. So for weeks, from mid-October through most of November, Earth went blind. We couldn't see 3I divided by Atlas. All the major observatories that had been tracking it were forced to wait. The data pipeline stopped. And here's the absolutely maddening part. This was almost certainly the most interesting period of the comet's entire visit. Based on the brightening trend, based on the CO2 chemistry, based on everything scientists had learned up to that point, this was when 3I divided by Atlas should have been most active. The perihelion phase, when the comet was closest to the sun and receiving maximum heating, should have produced peak outgassing. The most dramatic dust production, possibly even fragmentation or major structural changes to the nucleus. And we missed it. Scientists on Earth were stuck in an enforced silence, waiting for the comet to emerge from behind the sun, wondering what was happening on the other side. It was astronomical FOMO, fear of missing out, on a cosmic scale. Here was only the third confirmed interstellar visitor to our solar system, doing its most interesting stuff, and we couldn't see any of it. But not everyone was blind. Act 6. The Watchers Beyond. While Earth sat in darkness, other eyes kept watching. Spacecraft scattered across the inner solar system, positioned at different angles, different locations, different vantage points that Earth didn't have, and they captured what we couldn't. ESA's ExoMars Trace Gas Orbiter was the MVP. This spacecraft, sitting in orbit around Mars, had one of the best views of 3I divided by Atlas during the blackout period. On October 17th, the day of the Mars flyby, TGO captured images of the comet from about 30 million kilometers away. These were the closest views any human spacecraft had ever obtained of an interstellar visitor. The images showed a bright, fuzzy nucleus surrounded by the expanding coma. The comet looked active and vigorous. The nucleus itself appeared as a bright point source, too small and distant to resolve individual features, but the surrounding cloud of dust and gas was obvious. Scientists could measure the coma's size, estimate the dust production rate, and compare it to earlier observations from Earth. Mars Express, another ESA orbiter, also attempted observations. Its instruments, NOMAD, Omega, and SpyCam, were designed to study the Martian atmosphere, not interstellar comets. But the mission team pushed the spacecraft to its limits, retargeting instruments and stretching them beyond their original design specifications to catch glimpses of the visitor. Not all the observations were successful, and some data was marginal, but the effort itself was remarkable. Engineers and scientists scrambling to turn Mars science instruments into comet detectors just so humanity wouldn't be completely blind during the blackout. And then there's the unconfirmed but tantalizing report from the Martian surface. On October 4th, a few weeks before the closest approach, NASA's Perseverance rover may have captured something in its images. Some reports suggest a streak consistent with the comet appeared in one of the rover's sky images. If confirmed, this would be the first time in history that a rover on the surface of another planet photographed an interstellar object. Think about that. A robot sitting on Mars designed to study rocks and search for signs of ancient life, accidentally becoming an interstellar comet photographer. The confirmation is still pending. The image needs more analysis to rule out cosmic rays, hot pixels, or other artifacts. But if it's real, it's another piece of the story. Another watcher beyond Earth that kept the vigil during the silence. Meanwhile, farther out in the solar system, Other spacecraft prepared their own observations. ESA's JUICE, Jupiter Icy Moons Explorer, was en route to Jupiter when 3I divided by Atlas passed through. JUICE attempted what mission planners called off-axis observations, where the spacecraft pointed its instruments slightly off its main trajectory to catch the comet. The data from these observations took time to downlink because of the vast distances involved and the spacecraft's limited communication bandwidth. But eventually, the data arrived, adding another perspective to the puzzle. NASA's Europa Clipper, also heading to Jupiter, joined the campaign. Space telescopes, including Hubble, continued opportunistic observations when geometry allowed. Even SWIFT, an X-ray telescope normally used to study gamma-ray bursts and distant galaxies, tried to catch high-energy emissions from the comet's coma. It was a distributed network of observers, a relay race choreographed by orbital mechanics, where Earth's silence was covered by spacecraft positioned at other locations around the inner solar system. The blackout from our planet became a showcase for interplanetary collaboration. While we couldn't see 3I divided by Atlas, our robotic ambassadors could, and they kept watch for us. Act 7, Dark Forest Whispers. During the blackout period, while scientists waited for data and the public followed whatever updates trickled in from Mars-based observers, something interesting happened in the corners of the internet and in one provocative academic paper. People started asking uncomfortable questions. The trajectory of 3I divided by Atlas was unusual. Not impossible, not even particularly unlikely from a strict orbital mechanics perspective, but unusual. The comet passed relatively close to Venus during its inbound journey. Then it passed relatively close to Mars. Its perihelion was at 1.4 AU, not far from Earth's orbit. And after perihelion, its outbound trajectory would take it past Jupiter's orbit. None of these were collision courses. These were close only in astronomical terms, millions of kilometers away. But they were closer than random chance might suggest for an object entering the solar system from an arbitrary direction. It was like threading a needle through multiple planetary lanes without hitting anything, but coming closer than you'd expect. One research paper took this observation and ran with it into speculative territory. The authors acknowledged up front that 3I divided by Atlas was almost certainly a natural comet. Everything about its composition, behavior, and appearance screamed comet, but they posed a provocative what-if scenario. What if an advanced civilization wanted to send a probe to survey a star system, and they wanted to do it quietly? You'd use a natural object as camouflage. You'd pick something that looks exactly like a comet because it is a comet, or at least a comet-like body. You'd use the sun's gravity for course corrections, a technique called a solar Oberth maneuver, to efficiently redirect your trajectory without expending fuel. And you'd do it while passing behind the sun, when the host system's inhabitants couldn't see you. The paper invoked the dark forest hypothesis, a concept from science fiction that suggests the universe is full of intelligent civilizations, but they all stay silent and hidden because revealing yourself is dangerous. Advanced civilizations might probe other systems using stealthy, natural-looking objects rather than obvious artificial spacecraft. To be absolutely clear, the mainstream scientific community does not believe 3I divided by Atlas is anything other than a natural comet. The CO2-rich chemistry, the dust activity, the brightening behavior, the spectroscopy, all of it matches what you'd expect from a comet that formed in the outer regions of an extrasolar planetary system and wandered for billions of years. There is zero evidence of artificial construction, propulsion, communication signals, or any kind of technology. But the paper's point wasn't really to claim 3I divided by Atlas is alien tech. The point was to highlight how the blackout period created a situation where certain hypotheses became temporarily unfalsifiable. If you're going to do something sneaky, doing it when Earth can't see you is the perfect time. And because we couldn't see the comet during its most active phase, we can't definitively rule out every wild scenario. It's a thought experiment, a reminder that the absence of evidence is not the same as evidence of absence. And it demonstrates how much we rely on continuous observation to understand what's happening in our solar system. The Dark Forest Whispers were mostly confined to Twitter threads, YouTube videos, and a handful of fringe articles. Most astronomers rolled their eyes and went back to analyzing actual data. But the speculation did serve one useful purpose. It emphasized the importance of the multi-spacecraft observation campaign. The fact that Mars orbiters, outer solar system spacecraft, and space telescopes kept watching during Earth's blackout is precisely what keeps wild speculation testable and grounded. If 3I divided by Atlas had done something truly anomalous during the blackout, changed trajectory in a way natural comets can't, emitted unusual signals, deployed objects, the Mars-based observers would have caught it. The fact that they saw a comet behaving like a comet is strong evidence that, yes, it's just a comet. The Distributed Observation Network is humanity's insurance policy against both missing crucial signs and entertaining unfalsifiable theories. Still, the timing of the blackout was undeniably dramatic. An ancient visitor from another star system, threading past multiple planets, reaching peak activity at the exact moment Earth goes blind. You can understand why some people's imaginations ran wild. Act 8. The Reappearance. Early December 2025. Ground-based observatories around the world began picking up 3I divided by Atlas, again as the comet emerged from behind the Sunday. It was like a curtain lifting after an intermission, revealing what had changed during the blackout. The comet was still there. It hadn't fragmented. It hadn't exploded. It was past perihelion now, heading outbound, still active but beginning to fade as it moved farther from the Sunday. Spectroscopy campaigns resumed immediately. Astronomers wanted to compare the pre-perihelion chemistry to the post-perihelion chemistry to see how the comet had changed. Did the extreme heating near perihelion alter the nucleus? Did the surface crust completely blow off, exposing deeper, more pristine layers? Were the gas ratios different now? These questions drove the observing campaigns through December and into early 2025. Preliminary data suggested the comet was still CO2 rich, though some teams reported slight variations in the CO2 to water ratio compared to earlier measurements. Whether this represented real compositional changes or just measurement uncertainties would take months of analysis to determine. The coma morphology, its shape and structure, also drew attention. Scientists looked for jets, asymmetries, or other features that might indicate active vents on the nucleus or rotational effects. Hubble Space Telescope observations attempted to measure the nucleus size more precisely. Earlier estimates, contaminated by the bright coma, had placed the nucleus diameter somewhere in a broad range from 0.325 to 5.6 kilometers. That's a huge uncertainty. The difference between a relatively small comet and a pretty substantial one. Dust production modeling and comparisons to 2I divided by Borisov suggested the nucleus was probably on the smaller end of that range, likely under 1 kilometer across. A sub-kilometer nucleus producing this much activity is actually pretty impressive. It means the comet is extremely active for its size, which makes sense given the CO2-dominated composition. CO2 sublimates more easily than water ice, so a CO2-rich nucleus can produce more gas and dust per unit surface area than a water-rich one. By late December, enough post-perihelion data had accumulated for scientists to start drawing conclusions. The comet had survived its close solar encounter without breaking apart. It remained active, though fading as expected. And most importantly, the detailed observations from Mars-based spacecraft during the blackout had provided crucial data on the comet's peak activity phase. The full story of 3I divided by Atlas was starting to come together. Act 9. What we almost lost. Here's what makes the blackout period so significant and why the Mars-based observations were so valuable. If we'd had to rely solely on Earth-based observatories, there would have been a complete data gap from mid-October through late November. We would have seen the comet approach, watched it start to brighten dramatically, and then lost track of it right before the climax. When it reappeared in December, we'd be left wondering what happened during those critical weeks. Did the brightening surge continue? Did it level off? Did the nucleus fragment? We wouldn't know. We'd have a before picture and an after picture with no idea what happened in between. But because Mars orbiters and outer solar system spacecraft maintained observations, we didn't lose the thread. The data might not be as detailed as what we'd get from Earth's largest telescopes, but it's there. Continuous coverage, no gap. The story stays intact. This incident highlights a crucial point about planetary science and particularly about interstellar object studies. Earth is not always in the best position to observe things in our own solar system. Having assets distributed across multiple locations, orbiters at Mars, spacecraft in the outer solar system, telescopes at different Lagrange points gives us observational resilience. When one location goes blind, others can pick up the slack. The 3I divided by Atlas blackout also revealed something about interstellar object intercept missions. Several teams ran feasibility studies during the summer of 2025 after the discovery. Could we launch a spacecraft to intercept 3I divided by Atlas and get close-up data? From Earth, the answer was a harsh no. The comet's trajectory and velocity meant that any spacecraft launched from Earth would need a delta V change in velocity of more than 24 kilometers per second to intercept. That's wildly beyond what our current propulsion technology can achieve for anything larger than a small CubeSat. We simply can't go that fast with conventional rockets. But here's the interesting twist. If you are starting from Mars, the delta V requirements dropped dramatically. A spacecraft stationed at Mars between July and September 2025 could theoretically intercept 3I divided by Atlas in October with a delta V around 5 kilometers per second. That's still challenging, but it's within the capabilities of existing spacecraft if one happened to be at Mars with fuel reserves and retargetable instruments. Of course, none of our Mars orbiters or landers are designed for this kind of rapid retargeting. They're locked into their primary missions, studying Mars. You can't just yank a Mars orbiter out of its orbit and send it after a comet on a few months' notice. The fuel requirements alone would be prohibitive, and the scientific instruments aren't optimized for comet studies. But the feasibility study made scientists realize something important. If we want to intercept future interstellar visitors, we need forward-deployed assets. Spacecraft parked at strategic locations, Mars orbit, the asteroid belt, Jupiter's vicinity, ready to be retargeted on short notice when a new ISO enters the solar system. Think of them as interceptor probes on standby, waiting for their moment. The window for catching 3I divided by Atlas from Mars was narrow, really narrow. By the time the discovery was made on July 1st and the interstellar nature confirmed in the following days, you'd have only about 2 months to plan, reprogram, and execute a retargeting maneuver. Realistically, that's impossible with current mission planning processes, which take months or years. But hypothetically, If you had a spacecraft at Mars that was already designed for this kind of rapid response intercept, with pre-approved protocols and autonomous decision-making capability, you could do it. Some researchers propose something called cacheable flyby kits, essentially pre-built, pre-approved mission packages that could be rapidly deployed when an opportunity arises. Think of it like emergency supplies. You don't know when you'll need them, but when you do, you need them fast. A mission architecture like Janus, small, agile spacecraft that can be built and stored, then launched quickly, might be the template for future ISO intercept attempts. The lesson from 3I divided by Atlas is clear. If we want to study these visitors up close, Earth is not the only launching point we should consider. Mars, Venus, even Jupiter could serve as waypoints for intercept missions, dramatically reducing the energy requirements and expanding our capability to reach these objects. But all of this is forward-looking. For 3I divided by Atlas, we had to settle for remote observations. And honestly, those observations were already revealing a comet unlike anything we'd seen before. Act 10, a comet that breaks the rules. Let's zoom out and look at the bigger picture of what 3I divided by. Atlas told us about interstellar objects and comet science in general. First, the early dust activity without strong gas emission lines challenged our understanding of how comets activate. Traditional models assume that water ice sublimation is the primary driver of comet activity. As the sun heats a comet, water ice near the surface sublimates, creating gas pressure that lifts dust off the nucleus. Other volatiles like CO and CO2 contribute, but water is usually the main player. 3I divided by Atlas flipped that script. It was releasing dust at large heliocentric distances without the corresponding water-driven gas emission. The CO2-dominated chemistry eventually explained this. CO2 sublimates at much lower temperatures than water, but it demonstrated that not all comets follow the water-centric playbook. Some are CO2 machines. And if they're CO2 machines, they behave differently, activating earlier, brightening faster, producing different dust-to-gas ratios. This has implications for how we identify and characterize comets, especially distant or faint ones. If we're looking only for water-related emission lines and ignoring CO2, we might miss or misclassify active comets. It's a reminder that diversity in the comet population is real and significant. Second, the chemical composition of 3I divided by Atlas added a crucial data point to our understanding of extrasolar planetary systems. Every ISO that visits us carries chemical signatures from its home system. By studying those signatures, we can infer what conditions were like in that distant protoplanetary disk billions of years ago. 3I divided by Atlas's extreme CO2 to water ratio suggests it formed in the cold outer regions of its home disk, far from its parent star. This is consistent with dynamical models that predict most ejected comets come from the outer zones of planetary systems, where gravitational scattering by giant planets is most effective. But it also raises questions about the diversity of planetary system architectures. How common are systems that produce CO2-rich comets? Do different stellar types produce different comet populations? We only have 3 confirmed interstellar objects so far: Oumuamua, Borisov, and ATLAS. That's a tiny sample size, statistically speaking, but already we're seeing diversity. Oumuamua was bizarre, elongated, tumbling, no visible coma, possible outgassing-driven acceleration. Borisov was more normal, a standard comet with CN and C2 emission behaving much like solar system comets. Atlas is CO2 rich and active at unusual distances. 3 objects, 3 different stories. Extrapolating from that, the population of interstellar objects drifting through the galaxy must be incredibly diverse, reflecting the variety of planetary systems and formation environments across billions of star systems. Third, the age estimate of 7.6 billion years forced scientists to reckon with the timescales involved in interstellar travel. Even at 58 kilometers per second, an insane speed by human standards, you cover less than 2 light years per million years. The closest star to us is over 4 light years away. If 3I divided by Atlas spent billions of years wandering, it could have traveled tens or even hundreds of light years, passing dozens of star systems along the way. And yet, for all that time, it remained frozen. The cold of interstellar space, barely above absolute zero, kept the volatiles locked in solid form. Only now, as it fell into the gravity well of our sun and received concentrated sunlight for the first time in potentially billions of years, did it wake up. It's like finding a frozen mammoth in the Arctic ice and watching it thaw. Except this mammoth came from another star. The preservation of volatiles over such enormous timescales is actually surprising. Cosmic rays and UV radiation from distant stars should gradually process and destroy surface ices. The fact that 3I divided by Atlas still had active CO2 and water ice suggests either the radiation damage was limited to a thin surface crust, or the object spent much of its journey in relatively protected environments, perhaps passing through dense molecular clouds that shielded it from radiation. Either way, it demonstrated that interstellar objects can carry pristine samples of their birth environments across vast distances and times. They're not just rocks, they're archives. Frozen libraries containing information about planetary systems that may no longer exist. Act 11, the Pre-Discovery Archive Problem. The TESS pre-discovery detection opened up a fascinating possibility that most people haven't considered. Right now, there are archives of astronomical images sitting on servers around the world, decades of sky survey data, millions of images taken by telescopes looking for asteroids, exoplanets, variable stars, supernovae, and everything else. Buried in those archives could be interstellar objects that no one has identified yet. Objects that passed through our solar system before we knew to look for them. Ghost trails in old data, waiting to be found. The TESS detection proved this isn't hypothetical. It happened, and it worked because someone had the idea to go back through the archive and look. Now, multiply that by every other survey telescope, every other space mission, every other archive of images taken over the past few decades. How many more interstellar visitors have we already recorded without realizing it? Several research teams are now developing algorithms to search through these archives automatically. Machine learning models trained to recognize the specific patterns of hyperbolic objects moving through the field of view. The goal is to create a catalog of pre-discovery detections, not just for 3I divided by Atlas, but for any ISO that might have passed through during the coverage period of various surveys. This is a complete paradigm shift in how we think about interstellar object discovery. Instead of waiting for new objects to arrive and hoping we catch them in real time, we can mine the past. We can retroactively discover objects that visited us years ago and extract whatever information the archive images contain. For 3I divided by Atlas specifically, researchers are checking archival data from Pan-STARRS, the Catalina Sky Survey, the Zwicky Transient Facility, and dozens of other surveys. Any dataset that covered the region of sky where 3I divided by Atlas passed between May and July 2025 might contain additional images. More data points mean better constraints on the orbit, better activity curves, better understanding of how the comet behaved as it approached. But the broader implication is that our count of interstellar visitors, currently 3 confirmed objects, might be artificially low. We might have already seen 4, 5, 10, or more without recognizing them at the time. The archive mining projects over the next few years could dramatically expand the population of known ISOs and give us a much better statistical sample to work with. And that statistical sample is crucial for understanding how common these objects are. Right now, estimates suggest that at any given moment, there might be 1 or 2 interstellar objects passing through the inner solar system. But those estimates are based on limited detections and a lot of assumptions. If we find that we've been missing most of them because they were too faint or because they passed through before we were looking carefully, we might need to revise those numbers upward. More interstellar objects means more opportunities to study the chemistry and dynamics of material from other star systems. It means more data points for testing theories about planetary system formation and evolution. And it means that what seemed like rare, special events, interstellar visits, might actually be relatively common. We just weren't paying attention. Act 12. The Astrometry Challenge. While the blackout period complicated observations, it also created an opportunity to test something important: non-gravitational acceleration. This is the phenomenon where outgassing from a comet creates a tiny thrust, like a rocket engine, that alters the comet's trajectory. It's subtle, but over time it accumulates and causes the orbit to deviate from pure gravitational predictions. Oumuamua famously showed non-gravitational acceleration, which sparked all sorts of speculation about what was causing it. Was it outgassing? Was it radiation pressure? Was it something else entirely? The debate still isn't fully settled, though most scientists favor outgassing as the explanation. For 3I divided by Atlas, the expectation was that it would also show non-gravitational acceleration given its obvious and vigorous activity. CO2 venting should create thrust. The question was, how much and in what direction? To measure this accurately, you need precise positional measurements over an extended time baseline. You need to track the comet before perihelion, through perihelion, and after perihelion, then compare its actual trajectory to what pure gravity predicts. Any deviation tells you about the forces from outgassing. The blackout period created a gap in Earth-based astrometry, precise position measurements, but spacecraft observations from Mars and elsewhere helped fill that gap. By combining pre-blackout Earth observations, blackout period spacecraft observations, and post-blackout Earth observations, researchers could construct a continuous astrometric timeline. Initial analysis suggested 3I divided by Atlas did indeed show non-gravitational acceleration consistent with CO2-driven outgassing. The magnitude and direction of the acceleration matched what you'd expect from the observed coma activity and the brightness surge. This was reassuring. It meant the comet was behaving as comets should, not exhibiting anomalous forces like Oumuamua did. But the final astrometric solution would take months to refine. You need to account for observer position, light travel time, relativistic effects, the gravitational influence of planets, and measurement uncertainties. It's painstaking work. And the accuracy of the final answer depends heavily on having good data coverage throughout the comet's passage through the inner solar system. The fact that the blackout period didn't create an unbridgeable gap in the astrometric record is a testament to the value of the multi-spacecraft observation campaign. Without Mars-based observations during those critical weeks, we'd have a much harder time constraining the non-gravitational forces and understanding how the outgassing affected the orbit. Act 13. The nucleus size mystery. One of the most basic questions about any comet is, how big is it? For 3, I divided by Atlas. This turned out to be surprisingly difficult to answer with confidence. The problem is that the nucleus, the solid body at the heart of the comet, is surrounded by the coma, a huge cloud of gas and dust. When you take an image of the comet, you're seeing the combined light from both the nucleus and the coma. Separating them is challenging, especially when the comet is active and the coma is bright. Early estimates place the nucleus diameter somewhere in the range of 0.325 to 5.6 kilometers. That's a factor of 17 difference between the lower and upper bounds. Not exactly precise. Hubble Space Telescope observations attempted to narrow this down by taking the highest resolution images possible and modeling the brightness distribution. The idea is to assume the nucleus is a point source, and the coma has a particular radial brightness profile. You fit the model to the data and extract the nucleus brightness separately from the coma brightness. Then you convert brightness to size using assumptions about the nucleus's reflectivity. But all of those assumptions introduce uncertainty. How reflective is the surface? Is it more like a dark, carbonaceous asteroid or a brighter, icy object? What's the shape? Spherical, elongated, irregular? All of these factors affect the size estimate. Dust production modeling offered another approach. By measuring how much dust the comet was producing and comparing it to other comets with known nucleus sizes, researchers could estimate 3I divided by Atlas's size indirectly. The dust production rate scales with the active surface area, which scales with the nucleus size. This method suggested the nucleus was probably on the smaller end of the range, likely under 1 kilometer in diameter, possibly as small as a few hundred meters. Comparisons to 2I divided by Borisov, which had a well-constrained nucleus size of about 0.4 kilometers, suggested 3I divided by Atlas might be similar or slightly larger. A sub-kilometer nucleus producing this much activity is impressive. It means the object has a very high active fraction, the percentage of the surface that's actively venting gas and dust. Some comets are mostly inert with just a few active spots. 3I divided by Atlas seemed to be active across much of its surface, which makes sense for a CO2-rich body where sublimation happens easily. But the lack of a definitive size measurement was frustrating. Media reports sometimes cited multi-kilometer estimates, which likely included significant coma contamination. The actual nucleus was almost certainly smaller, but pinning down an exact number required more data and better models. This is a common problem in comet science. Until you send a spacecraft to actually see the nucleus up close, like the Rosetta mission did with Comet 67P, you're stuck with indirect estimates. And for interstellar objects moving at 58 kilometers per second, sending a spacecraft is extremely challenging. Which brings us back to the INTERCEPT mission feasibility studies and the dream of actually visiting one of these objects someday. Act 14. The trajectory threading. Let's talk more about the trajectory, because it really is remarkable when you map it out. 3I divided by Atlas entered the solar system from interstellar space on a path that brought it relatively close to Venus during the inbound journey. Not dangerously close, but closer than random chance might predict. Then it passed Mars at about 30 million kilometers in mid-October. Then perihelion at 1.4 AU just inside Mars's orbit. Then, on the outbound leg, its trajectory would carry it past Jupiter's orbital distance, though not particularly close to Jupiter itself at that moment. From a purely statistical standpoint, this isn't impossible. The solar system is big, and there's a lot of empty space. But it is a little bit unusual for a hyperbolic object to pass this many planetary zones without coming from a specifically targeted direction. Most interstellar objects entering the solar system would miss the inner planets entirely, passing through the outer solar system or approaching from angles that don't bring them near rocky planets. The fact that 3I divided by Atlas threaded through the inner system, passing multiple planetary orbits, made its geometry somewhat special. This is what sparked the speculative papers about deliberate trajectories and solar Oberth maneuvers. If you wanted to design a trajectory that samples multiple planets in one pass, you'd aim for something like what 3I divided by Atlas did. Inbound past the inner planets, perihelion for velocity boost, outbound toward the outer system. But here's the thing. Orbital mechanics is governed by gravity and momentum. You can't just choose an arbitrary trajectory through the solar system. Your trajectory is determined by your velocity and direction when you enter the sun's gravity well. And for 3I divided by Atlas, the incoming velocity and direction were consistent with an object that had been wandering interstellar space for billions of years, encountering random gravitational perturbations from passing stars. In other words, the trajectory was almost certainly the result of chance. The comet happened to enter from a direction and speed that brought it through the inner system. It wasn't aimed. It wasn't designed. It just happened. But the fact that people even ask the question highlights how little we still understand about the population of interstellar objects and how often they visit us. If interstellar visitors are rare, then any one visitor's trajectory might seem special or unlikely. If they're common, then the occasional one that threads through the inner system is just statistics at work. Given enough visitors, some will have interesting paths. The trajectory debate also underscored the importance of getting better statistics. We need to detect more ISOs, track their trajectories, and build a database of entrance velocities, directions, and paths through the solar system. Only then can we say with confidence what's typical and what's unusual. For now, 3I divided by Atlas's trajectory remains an interesting data point. Not anomalous enough to demand exotic explanations, but interesting enough to warrant attention and follow-up studies. Act 15. What Mars Revealed. Let's circle back to what the Mars-based observations actually showed during the blackout period, because this is where the real gold lies. ExoMars Trace Gas Orbiter captured the best images. But what did those images tell us? First, the coma structure. The images showed an asymmetric coma, not perfectly round, but elongated in one direction. This suggested that the dust and gas emission wasn't uniform across the nucleus. There were probably active jets or vents on specific parts of the surface, creating a directional flow of material. This kind of asymmetry is common in comets. The nucleus rotates. Different parts of the surface receive different amounts of sunlight depending on the orientation, and active vents can be concentrated in certain regions where fresher ice is exposed or where surface cracks provide easy escape routes for gas. By tracking how the coma shape changed over time, both from Mars-based observations and from before and after Earth observations, scientists could start to constrain the rotation period of the nucleus and the location of active regions. This is called coma morphology analysis, and it's a powerful tool for understanding the nucleus without actually resolving it in images. Second, the brightness measurements. The Mars observations during the blackout captured 3I divided by Atlas at or near peak activity. The brightness level during this period confirmed that the supergeometric brightening continued through perihelion. The comet didn't plateau or fade prematurely. It ramped up exactly as the CO2-dominated chemistry predicted. This validated the outgassing models and gave confidence that scientists understood what was driving the comet's behavior. If the Mars data had shown something unexpected, a sudden drop in brightness, or a fragmentation event, or wildly different colors, it would have forced a re-evaluation of the models. Instead, the data matched expectations, which is actually a win for science. It means the models work. Third, the spectroscopy attempts. Mars Express's instruments weren't really designed for comet studies, but they tried anyway. The data quality was marginal, but some preliminary results suggested continued CO2 emission during the perihelion phase, consistent with earlier JWST measurements. The signal-to-noise ratio wasn't great, so these results needed to be taken with caution, but they added another piece to the puzzle. And fourth, the temporal coverage. The Mars observations captured images and data at specific times during the October window, creating timestamps that could be correlated with ground-based observations from before and after the blackout. This temporal coverage was crucial for building a continuous activity curve, a graph of how brightness changed over time. Without the Mars data, the activity curve would have a flat gap where we had to interpolate between the last Earth observation in October and the first Earth observation in December. With the Mars data, we could fill in the gap with actual measurements. Not as many measurements as we'd like, but enough to constrain the shape of the curve. This matters because the shape of the activity curve tells you about the physical processes happening on the nucleus. A smooth curve suggests steady sublimation. A curve with spikes or jumps suggests sudden events, maybe a section of crust breaking off or a new vent opening up. By filling in the blackout period, the Mars observations helped scientists understand whether the comet's behavior was steady or episodic. Act 16. The network effect. The 3I divided by Atlas observation campaign demonstrated something that's becoming increasingly important in astronomy: the network effect. No single observatory or spacecraft captured the complete story. But by combining data from dozens of telescopes, multiple spacecraft, and observers around the world and across the solar system, a complete picture emerged. Ground-based telescopes in different hemispheres provided coverage as Earth rotated. Space telescopes like JWST, Hubble, and TESS contributed spectroscopy, high-resolution imaging, and pre-discovery detections. Mars orbiters filled the critical blackout gap. Outer solar system spacecraft added additional viewing angles and longer wavelength observations. Each piece of data, by itself, was incomplete. Each telescope had limitations: wavelength coverage, sensitivity, resolution, viewing geometry. But layered together, they created a multi-dimensional dataset that no single instrument could provide. This is the future of astronomy, especially for time-sensitive or geometry-dependent phenomena like interstellar object flybys. You can't rely on one telescope to capture everything. You need a distributed network with different capabilities and locations working together. And you need coordination. Someone has to organize the campaign, distribute target information, schedule observations to avoid gaps, and compile the data afterward. For 3I divided by Atlas, this coordination happened through a combination of formal channels, official observation proposals to major telescopes, and informal channels, astronomers emailing each other, posting updates on Twitter, sharing preliminary data before publication. The community responded remarkably well. Within days of the discovery, dozens of telescopes were pointed at 3I divided by Atlas. Within weeks, coordination networks were established to optimize coverage and avoid redundancy. And when the blackout period hit, the spacecraft teams were ready with their own observation plans. This kind of rapid, distributed response will be essential for future interstellar visitors. We now know they arrive with little warning. Detection typically happens when the object is already inbound and relatively close. You have weeks to months to gather data before the object reaches perihelion and starts heading back out. Miss that window, and it's gone forever. The network effect maximizes the science return during that brief window, and it ensures that even when one part of the network goes dark, like Earth during the 3i divided by Atlas blackout, other parts can compensate. Act 17. The population models revisited. After 3i divided by Atlas, researchers updated their interstellar object population models. These models attempt to predict how many ISOs are passing through the solar system at any given time, where they come from, how old they are, and what their properties might be. Before 3i divided by Atlas, the models were based primarily on Oumuamua and Borisov. 2 data points, not much to work with. Adding a third ISO with different properties, older, CO2-rich, higher velocity, significantly improved the constraints. The updated model suggested several things. First, the arrival rate of detectable interstellar objects in the inner solar system is probably around 0.2 to 2 per year. That's a wide range, but it's based on the detection rate so far and various assumptions about how many objects we're missing because they're too faint or approaching from unfavorable angles. Second, the population is indeed diverse. The models now incorporate different compositional families. CO2-rich objects like 3i divided by Atlas, water-rich objects like Borisov, and potentially other categories we haven't seen yet. The diversity reflects the variety of planetary system architectures and formation environments across the galaxy. Third, the age distribution is broad. Some interstellar objects are relatively young, a few 100 million years old, recently ejected from their home systems. Others, like 3i divided by Atlas, are ancient, billions of years old, wandering for most of the history of the universe. The age distribution tells you about the dynamics of planetary systems over time and how ejection rates have varied throughout galactic history. Fourth, the velocity distribution peaks around 30 to 40 kilometers per second, but includes outliers like 3i divided by Atlas at 58 kilometers per second. Higher velocity objects are less likely to be captured or slowed down by encounters with stars, so they tend to be older. They've been moving fast for so long that they've traveled farther and are more likely to enter our solar system from random directions. And fifth, the models predict that we should start seeing more ISOs as our detection capabilities improve. Next generation survey telescopes like the Vera-C, Rubin Observatory, which will begin operation soon, will scan the sky far more comprehensively than current surveys. They'll detect fainter objects and catch things earlier in their approach. The prediction is that within a decade, we might be detecting several interstellar objects per year. Instead of rare events, they'll become routine. And that routine detection will enable systematic studies of the interstellar object population, turning individual curiosities into a statistical sample we can analyze for trends and patterns. Act 18. The composition mystery deepens. Let's dig deeper into the chemistry, because there are still unresolved questions about what 3i divided by Atlas's composition actually tells us. The CO2 to water ratio of 7.6 is extreme, but how did it get that way? One hypothesis is formation location. If 3i divided by Atlas formed far from its parent star, beyond the CO2 ice line but still within the planetary system, it would naturally incorporate more CO2 than water. The outer regions of protoplanetary disks are cold enough for CO2 and CO to freeze out before water does, so bodies forming there would be enriched in these volatiles. But There's a problem with this hypothesis. Most planetary system models suggest that comets forming in the outer disk would be ejected by gravitational scattering from giant planets. And those comets would typically have a mix of volatiles, some water, some CO2, some CO, some methane. A ratio as extreme as 7.6 is hard to explain by formation location alone. Another hypothesis is surface processing. Over billions of years in interstellar space, radiation could preferentially drive off lighter molecules like water, while leaving CO2 behind. UV photons and cosmic rays can break apart water molecules and give them enough energy to escape, especially from a small comet with low gravity. CO2 is heavier and might be more resistant to this kind of loss. But this hypothesis also has problems. If radiation was stripping off water, you'd expect the comet to be mostly inactive or to show signs of severe surface processing, a thick, radiation-damaged crust. And while 3I divided by Atlas did show early dust activity suggesting some kind of processed layer, it also had vigorous outgassing, indicating that volatiles were still abundant. A third hypothesis involves the parent star's properties. If 3I divided by ATLAS formed around a more massive star, an A or F-type star rather than a Sun-like G-type, the protoplanetary disk would have been hotter and more irradiated. This could create different chemical gradients, favoring CO2 over water in certain zones. Or maybe it's a combination of all three. The comet formed in a CO2-rich zone around a specific type of star, got ejected into interstellar space, spent billions of years losing some of its lighter volatiles to radiation, and ended up with the extreme chemistry we see today. The truth is, we don't know. The sample size is too small. With only 3 interstellar objects, and only 2 of them showing significant comet-like activity, we can't say what's typical and what's unusual. Maybe 3I divided by Atlas represents a common class of CO2-rich interstellar comets. Maybe it's a rare outlier. We need more data. And that brings up another point. The importance of detecting ISOs early enough to get JWST and other major facilities pointed at them. The detailed spectroscopy that revealed 3I divided by Atlas's CO2-rich chemistry came from JWST observations in September. If the comet had been discovered later, or if JWST had been unavailable due to scheduling conflicts, we might have missed that crucial measurement. Future interstellar object studies will need to prioritize rapid spectroscopic follow-up. Discovery, confirmation, and spectroscopy should happen within days if possible. Every day of delay is a day lost in the brief window before the object fades or moves into unfavorable geometry. Act 19. The albedo question. Albedo is the measure of how reflective a surface is. Snow has high albedo. It reflects most of the sunlight that hits it. Charcoal has low albedo. It absorbs most of the light. For comets, albedo tells you about the surface composition and how much processing the surface has undergone. For 3I divided by Atlas. Estimating the albedo was tricky because the nucleus was never clearly resolved from the coma. But by comparing the brightness of the comet to models and making assumptions about the coma's contribution, researchers estimated the nucleus albedo at somewhere around 4 to 6%. That's pretty low. It means the nucleus is dark, absorbing most of the sunlight rather than reflecting it. For comparison, fresh snow has an albedo of 80 to 90%. Even dirty snow is around 40%. At 4 to 6%, the nucleus of 3I divided by Atlas is darker than asphalt. This low albedo is actually typical for comet nuclei, and it's consistent with surfaces that are rich in dark carbon-based materials, like the radiation process crusts we've been talking about. When organic molecules are exposed to UV radiation and cosmic rays for extended periods, they break down into complex terry substances that are extremely dark. This is called radiation darkening, and it's well documented in meteorites and in situ observations of other comets. So the low albedo supports the idea that 3I divided by Atlas's surface had been heavily processed over billions of years. The outer layer was darkened and altered by radiation, creating a protective crust over the interior ice. But here's an interesting twist. Low albedo means the surface absorbs sunlight efficiently. That absorbed energy heats the nucleus, which drives sublimation. So a dark surface might actually promote activity by making the comet heat up faster as it approaches the Sunday. For 3I divided by Atlas, this could explain part of the supergeometric brightening. The dark surface absorbed sunlight efficiently, heating the subsurface layers where CO2 ice was buried. The CO2 sublimated rapidly, cracking the overlying crust and creating vents. Those vents released gas and dust, further exposing fresh material which absorbed even more sunlight, creating a feedback loop. It's a scenario where the surface processing that occurred over billions of years in interstellar space actually set the stage for vigorous activity once the comet entered the inner solar system. The radiation damage didn't kill the comet, it primed it for an explosive awakening, Act 20, when silence ended, December 5th, 2025. That's when Earth-based observatories got their first good look at 3I divided by Atlas after the blackout. The comet had emerged from behind the sun, now on its outbound trajectory, past perihelion, heading back toward interstellar space. Telescopes in Chile and Hawaii were the first to reacquire it. The images showed a comet that looked similar to before, still active, still producing a coma, but noticeably fainter than at perihelion. This was expected. As the comet moved farther from the sun, it received less heating. Sublimation rates dropped, and the coma shrank. Spectroscopy campaigns restarted immediately. Teams wanted to measure the gas composition post-perihelion to see if anything had changed. Had the CO2 dominance persisted? Were there signs of water-rich layers now exposed after the perihelion outburst stripped away the outer surface? Initial spectra still showed strong CO2, though some teams reported slightly different ratios compared to the pre-perihelion data. Whether this was real compositional evolution or just measurement variability would take careful analysis to determine. The coma was fainter now, which made spectroscopy more challenging. Lower signal means more noise in the data. Imaging campaigns focused on coma morphology. Scientists looked for jets, fans, or other structures that might indicate specific active regions on the nucleus. Some images showed faint streaks or asymmetries in the dust distribution, hinting at rotational modulation, the nucleus spinning and exposing different active areas as it rotated. Attempts to measure the rotation period by tracking brightness variations over time yielded preliminary estimates around 6 to 8 hours, but the data was noisy and the exact value uncertain. For reference, most comet nuclei rotate with periods of a few hours to a few days, so this estimate was plausible but not definitive. Astrometry continued as well. Precise position measurements allowed refinement of the orbit and better constraints on non-gravitational acceleration. The goal was to match the observed trajectory to models that included outgassing forces, confirming that CO2 venting produced the expected thrust and trajectory deviation. And slowly, over December and into early 2025, the full dataset came together. Pre-discovery TESS images, Earth-based discovery, and early characterization. JWST spectroscopy, the approach to Mars. The Mars Orbiter observations during the blackout, the post-perihelion reacquisition and follow-up, dozens of telescopes, multiple spacecraft, hundreds of individual observations. The curtain had lifted, the silence had ended, and the story of 3I divided by Atlas could finally be told in its entirety, bringing it all together. So, what does it all mean? What did we learn from this ancient CO2-rich wanderer that briefly visited our solar system and then disappeared behind the sun at the worst possible moment? First, we learned that interstellar objects are diverse. We can't assume they'll all look like Borisov or behave like Oumuamua. Each one brings its own story, its own chemistry, its own mysteries. 3I divided by Atlas was a CO2 comet, active at unusual distances, brightening beyond predictions and carrying chemical signatures from a planetary system that existed billions of years ago. That diversity is a feature, not a bug. It reflects the incredible variety of planetary systems across the galaxy. Second, we learned that observation geometry matters. The blackout period wasn't a failure of our telescopes or our techniques. It was a reminder that Earth is not always in the right place to see everything that happens in our own solar system. Having distributed assets, spacecraft at Mars, probes in the outer system, space telescopes at Lagrange points gives us resilience. When one viewpoint goes dark, others can fill the gap. The success of the Mars-based observations during the blackout proved the value of this network approach. Third, we learned that pre-discovery archives are gold mines. The TESS detection weeks before the official discovery showed that we've probably been recording interstellar visitors for years without realizing it. Mining those archives could expand our sample of known ISOs and give us earlier warning of future visitors. Every extra day or week of advance notice is time we can use to plan observations, mobilize resources, and potentially even position spacecraft for better views. Fourth, we learned that rapid spectroscopic follow-up is essential. The JWST spectroscopy that revealed the CO2-rich chemistry was the key to understanding 3I divided by Atlas. Without that data, we'd have been left guessing about what made this comet so active and so unusual. Future discoveries need immediate spectroscopic characterization from major facilities. The window is brief, a few months at most before the object fades or moves into poor observing geometry. Fifth, we learned that intercept missions are possible, at least theoretically, if we position assets correctly. The feasibility studies showed that launching from Mars could have intercepted 3I divided by Atlas with reasonable delta V. We didn't have a spacecraft in position to do it this time, but we could in the future. Forward-deployed interceptor probes, pre-positioned at strategic locations and ready for rapid retargeting, could turn interstellar object flybys into up-close encounters. And sixth, we learned that even when we can't see something directly, even when geometry or timing works against us, even when there's a blackout, we can still piece together the story. The culmination of before and after Earth observations, during blackout spacecraft observations, archive mining, and detailed modeling allowed scientists to reconstruct what happened to 3I divided by Atlas during those crucial weeks in October when it was hidden from view. The comet didn't vanish. It was never gone. It was just behind the curtain for a while, and when the curtain lifted, the story was there, waiting to be read in the data. 3I divided by Atlas came from another star system, traveled for billions of years through the cold darkness of interstellar space, woke up as it fell into our sun's gravity well, threaded past Venus and Mars, reached peak activity behind the sun where Earth couldn't see, and then emerged on the outbound leg, gradually fading as it headed back into the dark. It's gone now. By mid-2025, it had faded below detection limits for all but the largest telescopes, and by 2026, it will be too faint and too far for any follow-up. It's returning to the interstellar void, resuming its billion-year journey to nowhere in particular. In a few million years, it might pass near another star system. Maybe someone there will see it, study it, wonder where it came from. But for a few months in 2025, it was ours to observe. We learned from it. We puzzled over it. We watched it disappear and then reappear. And we added one more data point to our growing understanding of what's out there. Wandering between the stars. The next interstellar visitor could arrive tomorrow or next year or a decade from now. When it does, we'll be ready. Better telescopes, better networks, better models. We'll catch it earlier, characterize it faster, and maybe, just maybe, we'll send something to meet it. Until then, 3I divided by Atlas remains the most thoroughly observed interstellar comet to date. The one that vanished and came back. The ancient messenger from a star system that's now just a faint point of light somewhere in the sky. The one that reminded us that the universe is full of wanderers, and sometimes they pass close enough for us to say hello. If you want to know what happens when the next interstellar object arrives, subscribe so you don't miss it.